Good afternoon, everyone, and welcome to our webinar. Thank you for joining us this afternoon. My name is Jumana Tariq Nabil Abdurrazik. I'm studying for a master's degree in petroleum engineering at University of Houston, and I will be your moderator this afternoon. Today, we're pleased to welcome Dr. Yasser Elshayeb, a very special guest from Egypt. Dr. Yasser Elshayeb got his bachelor's degree in mining engineering from Cairo University in 1990 and had his PhD from Nancy School of Mines in France on the contribution of fuzzy logic to geotechnical risk assessment of some ancient tombs at the Valley of the Kings in Egypt. He had a major role in setting up the Euro-Mediterranean policies and dialogues on higher education, research, innovation, and culture. Dr. Yasser currently works as a professor of engineering at the American University in Cairo. And today he will be sharing with us his expert opinion on quantitative data analysis. Please feel free to send your questions in the chat box, and we will answer as many questions as possible. With that, I ask you to give your full attention to Dr. Yasser Elshayeb and help me in welcoming him. Please welcome Dr. Yasser Elshayeb. Hi, Dr. Yasser. Thanks for joining us again today to pick up where we left off in the quantitative data analysis course.
Hello, Jumana. Thank you very much for the introduction. Thank you, everyone, for being here. Today, we are going to have a heavyweight, difficult session. Exploratory data analysis, which is part of the quantitative data analysis, is, I would consider it something quite heavy, it needs a lot of attention, because there is a lot of concepts that needs to be understood before embarking on doing anything in real. And in this session, I will look into two of the tools that we usually use for exploration. And when I speak about exploration, it's like exploration of the data. So we will not make any prediction. We will just try to understand the underlying, this is a term that we use, understanding the underlying structure of the data itself. How the data is structured together, what are the relationships between the variables, how can we understand how those many variables and how those many individuals that are in my data matrix are behaving together, are relating to each other, are working together. All of this we will this is what we call actually in quantitative data analysis as structural understanding. Sometimes we call it the summary of or summarizing the data. Sometimes we call it exploration. Sometimes we call it interdependence methodologies. But anyway, it's at the end of the day, the objective is to understand how this data is related to each other. And again, I'll be using here the component principle component analysis, and also the clustering analysis, and I will go in them one by one, slowly by slowly. One of the rules, one of the problems that we have in data analysis is that once the dimension of the data goes beyond 3 variables, it is very difficult to understand how it is behaving. Let me give you an example. We are 48 now participants in the in this webinar. Suppose that we have had measured for those 48 individuals, we have measured their height, their weight, their age, and the number of children that or the number of cars that everyone has. So we have 4 variables. Now, if I would like to look into this this data for 49 individuals, I will just, the easiest thing is to have the a numbers line, like going from 0 to 200, and I will put the height of every individual on that line. And I will have just a line to look at, and I will say, well, you know, there is a lot of people around 170 centimeters. There is a lot of people around 180 centimeters. There are less people around 150 centimeters, and so on and so on. I will call this a univariate analysis. I'm looking into the data. I'm just trying to understand how it is dispersed, how is it variable, what's its variability around that one single variable. Then I would like to incorporate into my analysis not only the height, but also the weight. So I will have another axis. So I'll have two axes now. Maybe I can, yeah, I can draw maybe this here now, a pen. So yes, so this line is for height, h, and it starts from 0. And I will have some points here, some points here, some points here, distributed anyway. Then I will add to this the weight of everyone. So I'll put another axis, and I will call it W, the weight. And for every individual that was here, that's the weight of that individual. And 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 so on and so forth. You have some points. We call it a cloud of points. That's fine. Well, afterwards, you can come back and say, well, you know, I have studied those points and I have seen a distribution for it. And we spoke about distribution before. The distribution of the height of the people is following a normal distribution, for example, function, or is following a beta function, or is following a log normal function, whatever, different functions. Then when you have weight and height and weight, you will say that, well, I see actually a trend. And you can conclude saying that, well, there is a line like this, and it says that whenever, globally speaking, generally speaking, with the increase of height, there is an increase of weight. Well, yeah, this is, I would say, very much acceptable. That's fine. And that's also interesting observation, an interesting description of the data that I have. Now, if I were to have a third parameters to be put here, and I will put here the third axis, which will be, we spoke about height, weight, and then age. And I'll call it A. For every point here, it will be a point in space of 3D. And I'm not a good guy in seeing things in 3D, actually. There are people that can do that, but I'm not one of those. So for me, in order to see things in 3D, I need to project it. So I need to take this cube of information and turn it a little bit to the left, to the right, maybe look at it from a plan point of view, or from an elevation point of view, or from a side view point of view. And this we do as well for example, machinery. I mean, when we draw a machine, when we draw anything, when we draw a key like this, in order to draw it in an engineering sense, we usually draw the plan, the elevation, and the side view. So we draw it from three different perspectives, because this is what we need to do. And usually I mean, human eye cannot see things really in 3D projected on 2D directly. You need some to develop yourself. But this is not the question, actually, or this is not the real problem, actually. The real problem is that if you would like also to add to this drawing, in order to understand or to see the data, if you would like to add to it as well the number of cars that a person has, or the number of children that a person has, is the gender of that person, the class of that person, the marks that he had in math or in physics or in petroleum engineering or in gas engineering. I mean, any other variable more than those three that you have here, that we have here on the screen, it is impossible actually to see it. You need to project this data. Sometimes we project it 2 by 2. So we take weight and height, then we take height and age, and then we take weight and age, and then we will take height and number of cars, and then weight and number of cars, and then age and number of cars. We usually do this because we are not able to see it in a 4D or 5D or 6D or 7D equation, or sorry, graph. And this is actually the main driver behind this methodology called principal component analysis. As I said now, I will consider that every variable that I have in my data matrix is a dimension, and it carries with it a number of information, a certain amount of information. To ease of calculations, I will say that every variable that is in my data matrix is carrying one variability, one variance, one V, let's call it a unit one. So if I have a matrix, if I have 10 variables, this means that I have 10 V, 10 variances. This means that in order to see this this cloud of information, where every individual has 10 coordinates, if we think of it in a cardinal way, every individual has 10 coordinates on the 10 variables, which are by themselves independent to each other. Then I need to look into a space of 10D. And of course, it's impossible to see a space of 10D. So how can we do that? The principal component analysis method, or the factor analysis method, what it does is that it reduces the number of dimensions. It actually, in using this methodology, we are able to project the data that we have in a cloud of 10D, sometimes 20D, sometimes 30D, because we have 30 variables that are in my data matrix. We try to project them on a space or on a plan of 2D, as this graph here indicates. You have points in a multi-dimensional space. We call it a cloud. So it's a multi-dimensional cloud, and you are trying to project those points on a plan. And what are the specifications of that plan? The specifications of that plan is that you don't want to lose much of the information. If you have 10 variables, and those 10 variables constitute 10D, 10 dimensions, 10V, as I said before, 10 variants. So you need that this plan will carry on something like 50% of the variability of the model. And in order to have 50% of the variability of the model, we actually rely on matrix mathematics. How do we do that? Actually, let me just take this this graph out and come back. Yes. How do we do that? Well, what we do in the principal component analysis is that let me go. Yes. What we do actually in the principal component analysis is that we work on the variance or covariance matrix, which is, I would say, we can think of it as the correlation matrix. Let me come back to the idea that we had. Remember when I said that we have three lines, three axes, and those axes are perpendicular to each other. And you have here one variable, you have here one variable, and you have here one variable. In order to see them, you need to see the relationship between this variable and that one. Or one way to see them is to see the relationship between this variable and that variable. And then you have another graph with this variable with that one. And then a third plot or a third graph with this variable with that one. So one with two, one with three, and two with three. And this will give you a fair, good idea about the relationship between the variables together. If you think of the, if you remember the correlation, when we spoke about correlation, I think not last time, maybe the time before. And correlation in mathematics, you can think of it as the behavior of a variable with respect to another one. So sometimes you have a positive correlation where variable x increases, variable y increases, or sometimes you have negative correlation, variable x increases, variable y decreases. And sometimes you have zero correlation, which is variable x increases and variable y is completely independent. It doesn't really have any effect on it. So those two variables, we call them independent variables. That's why in the last slide here, I spoke about the transformation of a set of correlated individual independent variables or dependent variables into a set of new uncorrelated variables, completely independent variables. And in mathematics, when we speak about independency, we speak about perpendicularity, i.e., if you have vector A and vector B, and the angle between vector A and vector B is 90 degrees, those two vectors are actually completely independent. And it happens as well in mathematics that if you have variable A and variable B that are completely independent, then they are, by definition, or by geometry, or by mathematics, they are perpendicular to each other. So what this methodology will do is that it will study all the variables that you have in your analysis, and it will produce a new set of independent variables that are perpendicular to each other that you can actually draw, and you can project your data on it, like this graph here. So I will invent a new plan, and this plan, I will define it with the most, I would say, suitable plan. And this most suitable plan, I will project everything on it, and I will be able to see the variables on it. I will be able to see the individuals on it, and I will be able to see like looking into my 10 variables as if I'm looking to them into a screen. I mean, I'm looking I'm like shedding some light on them, and I'm seeing the whole cloud of 10D in a reduced space that I can see it with my bare eyes, because I cannot see the 10D. I have to see 2D only, or 3D sometimes when we are quite clever. How do we do that? We do that actually by looking into the correlation matrix. And why the correlation matrix? Because as I said before, the correlation matrix is a way to see the relationship between variables and each other. Okay, they are independent. They are, by definition, all variables that are in the data matrix are independent. The weight and the height are completely independent, but there is a correlation between them. So they are, I mean, you cannot actually calculate height based on weight. You can have expectations, but you cannot calculate the real height based on the real weight. But we know that there is a correlation between them, so we will consider this correlation as the relationship between the two variables. As I said before, the variability in the model is equal to the number of variables. So if I have 10 variables, then this means that I have 10 variability in the model, a sum of 10 variability in the model. If I have 15 variables, then I have 15 variability in the model. We can call it the order n of complexity of the model, or the number of variables, or whatever we will call it. Now, what we will do is that we will calculate the correlation matrix, and then we will calculate also the eigenvalues and the eigenvectors of that matrix. And as you definitely know, and I'm sure that you know that in mathematics, eigenvalues and eigenvectors are calculated usually on a square matrix. Correlation matrix, by definition, is a squared matrix as well. Because in a correlation, I mean, if I have 10 variables, then I have 10 columns, I have 10 rows, and then in between I have the correlation between each variable and the other one. I will show you a correlation matrix right afterwards. So this methodology says that the eigenvalues and the eigenvectors of that correlation matrix are actually a projection of the data variables on reduced spaces. And the value of the first and the second and the third eigenvalues are the transformation of the variability in the model into a new set of variables. We call them components. That's why it's called the principal component analysis. And we can actually project them on a reduced space of 2D, for example. So I have a 10D variability, and then I can reduce them into 2D variability. And I will lose, of course, some of the information. I mean, in 10D, you have 10 variability. You can draw them on a 2D plan, and the amount of loss that you will have is sometimes 30%, sometimes 40%, sometimes 20%, which is a very good thing. So you reduce the space from 10D to 2D with some losses of information, but it's better than not able to seeing it at all. This is what's the principal component analysis about. I know that what I'm saying now is completely theoretical, but I will show you right afterwards how to do this with R, so we can work with it. This is, for example, how just schematically how we do it. Suppose that I have 1, 2, 3, 4, 5, 6. I have here 6 variables, and every one of those variables is counting for 1 variability in the model. So this model, the amount of variability in it is 6. I can say that I have 6D graph that I need to see, that I need to look at. Now, with the principal component analysis, and this is the result of the analysis here, one of the results of the analysis here, this graph tells me that I have worked on the correlation matrix, and I have normalized the correlation matrix, and I have obtained the eigenvalue and the eigenvalues and the eigenvectors of that correlation matrix. And the first eigenvalue is counting for 40% of the amount of variability that is in here. The second one is counting for 20% of the amount of variability that are in here, which means that if I will project all the points that I have on a plan that is defined by this axis and this axis, I will have something like 60% of the data or of the variability that are in the model. Now, if I will look into the 6 variable here, I would see that it counts for something like maybe 3 or 4% of the amount of variability that I have in the model. While I started at the beginning with every variable having 1. So now I have less than 1 here, and I can simply discard. This is as well another graph that shows the relationships between all those variables. This graph is a projection of the 6D data matrix that I have here, that I used here, is a projection on the first axis and the second axis, the first eigenvector and the second eigenvector. And it says that the first eigenvector, it contains 38%, as it was saying here. It's something about 40%. So it's actually 38.63%. The second one counts for 19%. As we were saying here, it's like less than 20%. So this model accounts for 38.63 plus 19.41% of the whole variability of that model. Now, how can we do that? How can we understand that? How can we extract information from that? Let me take you to R, to the software called R, and let me show you how can we do this, and we will of course discuss it afterwards. So I'll open my R here, and I will simply clear everything that I have because I was working on it. Yes. Now I will clear also the environment. I hope that in the last week or so, you have started working with R, you have downloaded it at least. Let me just skip for a second to open the light. Yes, okay. So my data is called air quality. And let me show you what my data looks like. This is my data. Air quality is a data matrix that has 1, 2, 3, 4, 5, 6 variables. The first variable is called ozone. Second variable is called solar R. Third variable is called wind, temp, month, and day. Actually, this is the data about, I think 153 measurements of the air quality in the city of New York, in the US. So every time we measure, we take those measures, 153 of them. Every time that we measure the ozone number, the solar radiation, and I don't know actually about the scale or the units, but ozone, it's a number. Then solar radiation, then the speed of wind in miles per hour, then the temperature in Fahrenheit, then the month, then the day. So this is my data, as simple as that. You can think of it, I mean, if you work in the oil and gas field, you can think of it as I'm measuring the water quality that I'm using for injection. I mean, what's the pressure of the water that I'm injecting in my oil field? What is the what's the pressure? What's the oxygen percentage? What's the chlorine percentage? What's the sulfur percentage, and so on? Or I'm producing oil from different oil fields, 153 oil fields, and for every oil field that I'm producing, I'm measuring certain values that are in my in the oil that is being produced. Okay, well, this is the air quality. Of course, if I would like to see one of those variables alone, it's very easy. As we said before, I mean, you can just like to draw a histogram of air quality and $, and then you take the ozone. Okay, that's it. So that's one variable that I'm drawing alone. So just I'm drawing ozone alone in order to see what is its distribution. Only one variable that I'm looking at a time. Then if I would like to see two variables together, then I have air quality, $, ozone, then tilde, comma, air quality string, and then wind. So if there is a relationship between the ozone, so on, and you have points like this. So you can look at it and you say, well, you know, I can see here a negative correlation. Usually, I mean, I can see here that a trend like going like this, a negative trend. So ozone increases, air quality decreases. Wind decreases. So I can say that whenever the ozone number increases, the speed of wind decreases, and vice versa, of course. And you can, of course, do a lot of those plots. I mean, you can plot air quality wind versus air quality temp. Is there a relationship between temperature and the speed of wind? I don't know. Well, this graph, well, I don't really see a trend in it. Maybe if we can look at it from a different angle, we can say that there is a ratio. But anyway, this is just to explore all the variables 2 by 2. As I said before, let's look into weight and height. Let's look into weight and age. Let's look into this and that. If we would like to see it in a 3D, then it become quite problematic. Now, correlation. I mean, I will start using correlation here, and I'm doing correlation between temperature and solar R. Or let's calculate actually the correlation between ozone and wind. So I'll replace temp by ozone. Sorry, and this one by wind. And it says minus 0.6. And it confirms actually what we have seen here. I mean, we've seen here a negative trend. So in mathematical terms, this negative terms, this negative trend is calculated as minus 0.6. If I will make the correlation, if I will calculate the correlation between the wind and the temperature, would I expect it to be less or more? I would expect it to be more on the 0 side because I don't see here anything. But let's try this. I'll copy this, I'll paste it, and I'll replace here wind and temp. Sorry. And you see to my surprise, I'm a bit surprised to see this number because it's not that small. It says that the correlation is minus 0.457. So the computer sees, or mathematically, we can see a trend that is also negative, that is going this way, but it's less evident than the trend that is in here. And of course, we can see this with our bare eyes, because this is minus 0.45, this is minus 0.6. So, okay. Well, there is also this graph that we can, this is the correlation matrix. Yes, it's here. Let's just focus on those numbers. This is the correlation matrix. So here you have the correlation between each variable and the others, and the 5 others. We have 6 variables in our model, 1, 2, 3, 4, 5, 6. And those are 1, 2, 3, 4, 5, 6 as well here. And here you have the correlation between everything and everything. So the correlation between ozone and solar radiation is 0.34. Correlation between ozone and wind is so. Correlation between ozone and temp is so. Ozone and month, ozone and day, and so on and so forth. So this is what we call the matrix of correlation, because it's a square matrix where you have on the lines, sorry, on the columns, titles, the name of variables, and on the row titles as well, the name of variables, and of, I mean, in the cells, if you think of it in an Excel format, in the cells, you have the correlation between each variable and the other one. And of course, correlation between temp and ozone is the same as the correlation between ozone and temp. So it's 0.698, and here it is 0.698. It's the same. It's we call this a symmetrical rectangular matrix. Sometimes we even don't write or simply don't calculate those numbers that are below this diagonal, because we know that those are the same ones. So in order to save time and to save effort, we just don't calculate them. But anyway, I mean, R is very fast, so it does just like that. I think we can also draw this correlation matrix. We can draw the graphs of the relationship between every 2 variables one by one here in this here. But for the sake of time, I will not go into that. Now, in order to do the principal component analysis, now we didn't do anything new. I would say new now. We've just worked on some plots to study the variables one by one. We've studied some of the variables 2 by 2, so 2 variables together, and then we had some correlation. And as I said before, in order to work on the correlation, in order to define those new axes and to reduce the variability in this model, we need to do the principal component analysis. And in order to do principal component analysis, you need to install some of the packages. I know that I spoke about package 4, but maybe it's the right time to speak about it again. Packages in R, as well as in Python, for those of you who are doing some programming in Python, are like add-ons. So those are tools, those are functions, those are commands that are developed by people like you and me, and are put in the disposal of everyone. So you can go online and download those packages, and of course use them, and of course know how to and produce something out of them. in order to download and install a package, you have two ways. Either you know the name of the package, so you just say install.packages, and then you have the name of the package. You go to the internet, and you can say packages in R, and you will have a lot of links to different packages. Yeah, you can see it here, the CRAN packages by name. So all of those are packages that are made by humans like you and me and are put here. You can download any of them, you can install it, and you can run it, and you can have data out of it. Now, how to run it, or how to install it in an semi-automatic way, I would say, you just go to Tools and then Install Packages. And if you know the name of the package, so for example, I know that it's called Facto Mine R, so I will start typing Facto Mine, and it appears here. I can just click on it and then install it. And when I will click, if I will click here, it will give me the same as just installing this package. Of course, I mean the package is installed at my on my computer, so it asks me if I want like to reinstall it and to restart the session again, and I will just say cancel for the moment. But in order to work with component analysis in R, and it's not the only way, there are many other ways, you can actually you have actually to install those two packages. One of them is called Facto Mine R, and the other one is called Facto Extra. So you just install those two packages. Then you go to packages here and make sure that those two packages are checked in. It's the same as mentioning here, library Facto Mine R, Facto Extra. And that's it. We will start the analysis now right away. So I'm telling my session in R that the data that I will be using is called air quality. Okay. Of course, the data that you use, the data matrix that you use, could be coming from Excel, it could be coming from CSV, it could be coming from SPSS, it could be coming from anything. But I'm just using air quality just for illustration purposes. And as I showed you before, this air quality, you have here function called head of air quality, and when you click on head for air quality, it will produce the very first 6 or 7, sometimes 10 lines of the data matrix. Of course, data matrix could be very long, but here it produces only 6 lines of it. So you can also make a summary of the of air quality. You can use the function summary, and the function summary will, for every variable, it will tell you what's the minimum values, what is the first quartile, the median, the mean, the third quartile, the maximum, and the number of missing values in it. So for instance, ozone, the minimum value of ozone that we have in our data matrix, the maximum value that we have is 168. The mean is 42.13. And we have 37 missing values. For wind, the minimum value is 1.7, maximum value is 20.7, the mean is 9.958, and we don't have any missing values. Well, that's just, it gives us just some information about our data. Now, in order to do the principal component analysis, there is a function called PCA, and this function will not work until you have installed this this package. So I'm just validating the function. So instantaneously it produced something here, and it produced also this image that we have here. And what is this image is telling me? This image is telling me that I have a plan. I mean, the computer is telling me I have a plan for you, and this plan has 60% of the variability of your model, and I'm projecting all the variables, original variables that you had on that plan. And if you look into this plan, if you look into those names of variables, and you will compare it to the correlation matrix that we had here, you will find a lot of interesting information. This plan or this graph tells me that ozone and temp are very much correlated to each other because they are, I mean, their lines are very close to each other. You can think of those lines as the level of perpendicularity between them. Remember when we were studying, when you were studying vector analysis, and when you have a vector X and a vector Y, and those vectors, they have a very small angle between them. So cosine of the theta of the angle that is separating them is actually approaching to 1. This means that those two variables are very much alike. It's the same concept we apply here. So whenever we have a very small angle, this means that those two variables are very much correlated to each other. And this should be confirmed actually in the matrix of correlation. So look at the correlation between ozone and temp, and it's about 0.7. I think it's the largest correlation that we have in this matrix. Yes, it's the largest number that we have in this matrix. If you will look into ozone and wind, you will see that the angle between them is very large. It's also approaching 1, but in the negative side, so it's approaching -1. So I would say that ozone or temp is very also negatively correlated with wind. You have here wind and ozone, or ozone and wind, and the correlation is -0.6. So it's high, not as high as ozone and temp, but it's in the negative side. Now let's look into temp and wind, and the correlation is -0.457. Not bad. Let's look into two other variables that in vector terms independent or looks independent. When usually two vectors are completely independent when the cosine of the angle that is separating them is approaching 0. So you have a 90-degree between those two variables. So let's look into the correlation between temp and solar R, for example. And I would expect that the correlation between temp and solar R is in the order of 0. Temp and solar R is 0.27. It's less, much less. Temp and day, -0.13. So it's also very, very low number. So in a nutshell, very rapidly, this graph is showing me all the correlation between all the variables that I have in my analysis. It's a projection of that correlation between all of those variables. It's a way that we use actually to reduce the amount of variables that we have in the matrix. So instead of showing you a correlation matrix like this, or a graph or a number of graphs that we have between every two variables together, I can only show you this graph. And if you will show me, or if I will show you next time, if I'll show you this graph, you will understand that what variables are correlated with each other, what are the variables that are not correlated, what are the variables that are negatively correlated, and so on and so forth. And remember that correlation means that those variables are behaving together. So it will give you more understanding of the behavior of that model or of that data matrix. Remember, at the beginning, we had 153 data points. We could have had 1,000 data points and 10 variables, and we would not be able to see anything. But with a graph like this, you are able actually to see to see it. Now, if I would like to show you as well the yes, the scree plot, which is no, not this one. I wanted to draw the scree plot, but I don't know why it's not actually working. Cancel, just give me a second. Sometimes you need to validate things again. Yeah, I think it will work this time. Yes, that's it. So this is the graph that I had in my presentation that says that the first eigenvalue is 40% or so. The second eigenvalue is 20% or so. The third eigenvalue is 30%, sorry, 20, less than 20%. The fourth one is about 15%, and so on and so forth. And you can have the choice to draw or to project your data on the first and second, first and third, second and third, whatever you want. I mean, usually we project it on the first and second because those are the ones that have most of the variability in the model. I'll go back to the presentation. So again, this is a transformation of the data, that instead of having 6 variables, everyone is contributing with 1. I have also 6 new variables, but not everyone is contributing with 1 variability. No, they are contributing with their eigen values. And this is a reduction actually of the amount of information or the amount of variability that we have in the model. I know that it's not easy to grasp all the information that I said in this half an hour or like 40 minutes, but I invite you, as always, as I did last time or the time before, that you go to the internet and type principal component analysis. Try to understand, try to look into the underlying calculations, how it's done. If you're good in math, then you can, of course, do the math yourself, or you can use a ready-made package like R to work on. Now, I will move to the next type of analysis that we have today, which are called cluster analysis. And actually, I will focus here on what we call the hierarchical cluster analysis. Hierarchical cluster or cluster analysis usually is a measure of similarity and dissimilarities. Again, let's take the same example of weight, height, and age, and number of children or gender. And I would like to see who is similar to who. Am I similar more to Dr. Ahmed or to Dr. Jumana? Is Dr. Jumana more similar to person X or to Yasser? This we don't know. Of course, we need to use all the variables that we have. We need to use all the information that we have, but we need to measure this similarity and dissimilarity. And the way that we do this is actually we work on distances. In mathematics, 2 points in space are similar to each other if the distance between them is approaching 0. 2 individuals that are unsimilar to each other, the distance between them is approaching infinity. And in order to calculate distance, you need an equation to calculate the distance. And the distance, of course, I mean, we have a lot of types of distances in mathematics. The most usual one is the Euclidean distance, which is the square root of the x of the coordinates minus coordinates of 0.1 minus coordinates of 0.2 squared, and then we take the square root of that sum. That's the equation. Nevertheless, there are many other people who have invented a lot of other distances that they say that it works better in this situation, it works better in that situation, and so. But I'm just putting it here for illustrative purposes. I'll just focus on the Euclidean distance that we usually work. So if I have 10 variables, then I have 10 coordinates on every one of those variables. And then if Jumana has also, if we are working in this, I mean, if we are in the same data matrix, then Jumana as well, she has 10 coordinates on the 10 variables. So for every x, or for every coordinate, I will take my my value, and I will take the value of Jumana, this one minus that one, squared, plus the second coordinate minus the second coordinate squared, plus third coordinate minus third coordinate plus squared, so on, so on, so on. And then we have the summation, and then we take the square root. So this will define the distance between me and Jumana in that space of 10 variables. And here is where we need to think about the scale of the distance. Because if variable x is measured in centimeters and variable y is measured in 1 or 2 number of cars, for example, 1, 3, then the effect of the difference in height will actually mask the difference in the number of cars. And this is where I will remind you of the second webinar that we had when I spoke about data preparation. Remember when we said that sometimes we need to standardize the data in order to have the data more or less working with the same in the same order of magnitude. I will show you how to do this in a minute with R. Now, this is how it looks like. This is how it works. And here I'm giving a very small example of the calculations. Of course, we can extrapolate that example to many other situations. Suppose that we have a grid like this, and this grid has 5 points in it, A, B, C, and D, and E. And we have this matrix, and this matrix tells us about the distance between every point and the others. So we have our 5 points here, our 5 points here, and we have the distances between them. So distance between A and B is 16, A and C is 1, A and D is 9, A and E is 10, A and A is of course 0 because it's the same point. Now, how this method will work. First point is that we look into this data matrix and we try to find the minimum distance. So the minimum distance that we found, that is not 0 of course, is 1. It's the distance between C and A. Difference between C and A is 1. Okay. Now, next step is we consider that C and A is one object. We replace C and A actually with one object. And this object is called object F, for example. And then we need to calculate the distance between that object that's called F and every other point that is in the system here. And the equation is the minimum. So we calculate the distance between A and B, C and B, and we take the minimum. And that minimum would be the minimum distance between that object, that new object, and the old object that, and the old object that is called B. I'll show you how does it work. I will reconstruct a new matrix, replacing A and C with F, and I will calculate the distance between F and every other point that is in the system. And then I'll search again another iteration for the minimum, and the minimum is 2, so it's E and B, and with E and B I will construct a new object called, I think, G, yes. And I will reconstruct again another matrix, and this matrix has F, which is actually A and C, has G, which is actually E and B, and the object D. And then I will do the same again. The minimum is 4, I'll calculate, and so on. And then I will find at the end that I have only 2 objects. One of them is called H, this one, and one of them is called G. Now, how can we draw this on a line? This is what we did, A and C. So we draw all the names on an x-axis, and then A and C, they had a distance of 1, and then we would consider them now as one object. Then B and E had 2, and then that object of A and C with D, it has 4, and so on. And that's the end of our analysis. So this graph tells me that I have here 5 objects. Those 5 objects, the two that are most similar to each other, that are very near to each other. Again, as I said before, similarity is the distance, the minimum distance, the small distance. So the ones that have smaller distance are A and C. So those we can see it here. And then this A and C with D, they have a similarity. And then B and E, they have a similarity. And then at the end, remember that we had actually here H and G. And this is what it says. This whole object has, well, it's somehow distant to that whole object. So this shows you that this and how this analysis is done. Now, of course, I mean, when you work with complex data analysis, large data, you don't afford to have only 2D. You have like 10D, 15D, and air quality, for example. I'll do the same analysis on the air quality, and I'll show you how it is. In air quality, you have like 6 variables, and you need to know the distance between them. I'll show you how this works with R as well. And here I have another variable. Let's clean everything. Yes. So here we have 3 different libraries to install and to work with. We have a package called cluster. We have a package called factoextra. We have a package called Magri TTR. I mean, they are there. So just make sure that those 3 variables, 3 packages are activated. And again, I'll work with the same data, which is called air quality, and I will just need to scale it. And scale here means standardization of that variable. And here I'm showing you the first 3 lines of that new data matrix. Remember that my original data contained number for ozone, number for solar R, number for wind, number for temp, and so on. Now it contains other numbers, and those numbers are standardized. Those numbers are actually bound between -3, let's say, and +3. So those are the boundary, and this is the effect of the scale. Now I will do this, and that's the original one. Let's compute the yeah, that's it. So this graph here, the cluster dendrogram, we call it dendrogram. This graph here shows me actually the 153 data points that I have in my data matrix. And it shows the similarity between the 153. Of course, I mean, it's 153, so we don't see a lot. We don't see a lot of it, but we can actually start, I mean, looking into it. I mean, I made some, yeah, this is a modified version of the same graph. And here you can say that, well, you know, I can divide my 153 data points into 4 clusters. This is cluster number 1, this is cluster number 2, this is cluster number 3, and this is cluster number 4. And individuals inside those clusters are very much alike, and they are different than the individuals that are in that in that data matrix. I'll show you another example because I know that this is not easy to look at because it's very too many. Lately, I've been interested. I was interested, me personally. I was interested in growing food at home. So when you grow food at home, we use a system called hydroponic. And in this hydroponic, you simply have your, you bring your seeds and you put the seed inside a solution. And in this solution, you put specific types of salts, and you put specific types of acids in order for that seed to grow, and you have a plant at the end. So actually, what I did here is that I have some data. Let me show you this data ahead, my data. Yeah, I have here some data that says that for plant number 1, you need to put that much of TDS. TDS, it's total dissolved solids, like salts. TDS after 2 weeks, TDS after 4 weeks, and then you have the pH, which is the acidity in the water, pH after, and then you have the name of the plant afterwards. Actually, I wanted to know if I would like to grow those plants together, which plants are similar to the others in terms of needs of solution and in terms of needs of pH. Which plants are the same or are similar to each other. And this is exactly what I did here. So not, I will just do it very rapidly. It seems that I have an error. Let me just show you the file, the final output. Maybe I'm missing something here. TDS and pH, that's it. That's the file. Yeah, that's the file. So this is the data that I have here. And I'm sorry, it's in Arabic. I mean, it's the name of plants are in Arabic. You have here the plant, the name of the plant in Arabic, the name of the plant in English, TDS at the beginning, TDS after 2 weeks, TDS after 4 weeks, pH at the beginning, and pH after 2 weeks. Which one of those plants are the same or are behaving the same that I can plant together? Actually, this is my objective. Now, this is what I've done, and this is the dendrogram that I have produced afterwards, and that's it. It tells me, I mean, this dendrogram is telling me if you want to plant 2 plants that are completely similar to each other, you have the I don't know the name in English. You have here the rucola, and the lettuce. So rucola and lettuce are actually very much alike. In another version, basil and lettuce are also very much alike. This could be something else. Okra and this plant that I don't know the name in English are also very much alike. So using this, I can actually know which plants that are similar to each other, so I can plant them together, so I can do them together. Now, let's stop here and I'll go to the very first slide. Exploratory data analysis. What we have done today is that we have explored the data. We did not predict anything. We did not project into the future. We did not forecast into the future. All what we did, or what we wanted to do, is actually to explore the data, to know in the principal component analysis, for example, what are the relationships between the variables? Where are the correlations? Where are the variables that are behaving together or behaving alike and moving together, or no, they are completely independent from each other in their behavior with respect to my data. So I didn't predict anything new. I just knew how things are in those variables. In the cluster analysis, I also didn't know anything new. I only knew which individuals are similar to each other. So I have this example of the 153, and then I saw the graph with them, all of them together, and I can actually understand that this individual number 50 is very much similar to this individual number 90, and I I could have done that if I have only one variable. I mean, when you have only one variable and a timeline, or sorry, a number line like this, you can see those numbers, that those individuals that are very close to each other. But when you have 6 variables like the example that we had, it's impossible to know that. But with the cluster analysis, you are able to see this similarity between those two. Your homework, if you would like to understand more, is to go online and search for principal component analysis, and forget about factor analysis is the very large name of the tool. Go online and search for principal component analysis. What are the mathematics that are underlined that I have mentioned? Just a few of it. Cluster analysis. What are the mathematics that are behind it, and how else also we can use. Of course, you will have a quiz for today. I know that it's not easy to understand like this very rapidly, and well, it's only 1 hour and 5-6 minutes that we spent here. Usually, I try to give this concept in like 3 or 4 lectures sometimes to go into the full details. But I also trust that you have an incredible tool called online that you can look into, and you have a lot of videos, a lot of YouTube videos that you can look into, and it will give you a lot of information about it. That's all for today. Jumana?
Thank you, Dr. Yasser, for this enlightening session. Now we'll move to answering some questions asked by our honorable audience. Someone says, what is normalization and what does normalized PCA mean?
Normalization means that all the numbers that we will be working with are within certain limit. And normalized PCA means that when we work with matrix of correlation, we know that all the numbers that we will work with are -1 to 1. I mean, there is nothing more. While if you work with a covariance or a variance matrix, you can have any number of variance or covariance. So that's it. So normalization means that you are transforming your variable from its original values, or sorry, you're transferring your values from its original number into a new number that are born with a minimum and a maximum. That is very well known.
Okay, someone's interested in knowing more about your take in the water injection project at the Gulf of Mexico.
Actually, I did that last time. I mean, last time I projected some of the data, and I showed how can we use it in some of the analysis, and the problem of missing variables and so on. I can come back to it maybe next time. Yes. Okay. Why not?
Okay. Someone says, what are the other ways of doing principal component analysis besides R?
A lot of software would do that. I mean, inside R, there are many different packages. If you will type on Google principal component analysis in R, you will find a lot of other packages that does the same that I did. And if you will also type principal tool for principal component analysis, you will find a lot of software that does that. SPSS does that. Stata does that. Almost all statistical analysis software does the same analysis.
Thank you, Dr. Yasser. That's about it for the questions today. It was a pleasure having you. Thanks for joining us. This was definitely a very insightful session, and thank you everyone for tuning in with us today. Dr. Yasser, we'd love to have you back. Thanks again.
Thank you so much, and see you next Tuesday.